That is controlling. Actually, I'm just going to forget about it, Dave.
Okay. Oops. Is your name pronounced Saeed?
Yeah.
Okay. Just want to make sure you can hear me. Well, we got one person.
Hello, Saeed.
Hello, Professor White. Can you hear me?
I can hear you. It's a pleasure to see you.
Yeah, me too. It's really amazing to talk to you actually from the camp, and I'm a little anxious about that. Mr. White, I want to ask you a question about the brain plasticity. First of all, I want to express my sincere thanks for this amazing course. You know, at the moment, I'm passing obligatory military service, and I'm soldier. But you know, this course has kept me alive, and you know, I really enjoy this course. And I just wanted to say thanks, and I don't know how to express my feeling, and it has changed completely my mind. But before I wanted to be a physical therapist, you know, my bachelor degree in exercise physiology, but after taking this course, I think I have a deep interest in neurobiology and the changes that happen in the brain after some mechanisms. So, to make a long story short, I want to ask a question about brain plasticity. In course era, I have taken another course in the past that was developmental psychology, and it was about brain plasticity. And I have learned in this course that as we get older, human being gets older, brain plasticity will decrease. I mean, learning a new language during childhood would be much more uh, easier to compare to when we get older. And I have learned a new concept, a new mechanism in your course about the brain synaptic plasticity. And the most important was about glutamate neurotransmitter and its effects on ionotropic receptors like NMDA and AMPA receptors. I'd like to know if we get older, this kind of mechanism will face some problems. I mean, glutamate neurotransmitters will not affect receptors as good as they affect in the past.
Thank you for the question, Saeed. I'm going to repeat the question just to be certain that everyone has heard it and understood. Saeed's question has to do with whether the mechanisms of brain plasticity continue to be robust throughout the lifespan, or might they change as we age? My answer to your question, unfortunately, is that we don't know the answer because it has been not studied to the depth that would be necessary to really address the question. There have been some studies that have looked at the expression of various molecules and mechanisms that are important for brain plasticity in older animals, and the result seems to be that there might actually be an upregulation of some of those mechanisms as we age. Now, this may be a compensation for the loss of synaptic connections and an overall decline of functional connectivity. It's not clear yet exactly what is happening as the brain enters the older stages of life, but I think we can expect that the brain is going to retain the basic mechanisms of plasticity, and if anything, there may be a way to try to continue to promote the maintenance of those mechanisms, even as circuits otherwise might be becoming somewhat dysfunctional and degenerative. I actually proposed to investigate this myself some years ago, but it was a challenge to get funding to do this kind of work. My hypothesis is that as we enter older life, we might enter another kind of critical period. That is, a period in which the brain is particularly sensitive to the impact of experience. But it may be critical for a different reason than the critical periods of early life. The critical periods of early life are a period of enhanced sensitivity due to the robust expression of these mechanisms that shape the structure and function of the brain. Now, I imagine that in older life, there may be a reactivation of some of these developmental mechanisms that are trying to deal with the onset of frailty as circuits become dysfunctional and somewhat degenerate in their connectivity. So that's the best that I can say at this point, Saeed, but I do think it's a tremendously important question. We need to understand how to optimize plasticity across the lifespan, and the rules of plasticity that we learn in early life or throughout much of adulthood may be modified by the factors that account for aging and age-related change in the brain. So I think this is an important question that we need to understand more through research in the years to come.
Yeah, thank you. And may I ask you the second question? Unfortunately,
yes, go ahead.
The problem to my connection, I cannot. Maybe I should check YouTube again. My second question is about the memory. You know, for example, we can remember a very tragic event in our childhood, or very enjoyable moment in our daily life. For example, for the first time when we fall in love with somebody. But we cannot remember many things that are happening around us. For example, I don't know, in the morning, what did I have, for example, for breakfast? And for memorizing the concepts, for studying the material of courses, I think it could be really critical, because if we know how to read something that we could remember forever, then with what time, could be really critical if you know that. But I would like to know if there is any research in this for the mechanism that can affect your memory, that you can remember some things forever. And as I learned in your course, the action potential that can cause every stimuli is not going to be more than the Nernst equation for sodium. So the amount of action potential is not going to be very big. So how a tragic event or a lovely event can affect our mind as deeply as we can remember it for the rest of our life?
Okay, thank you, Saeed. So Saeed's second question is about memory, and how is it that some memories stick with us throughout our life and others don't? And Saeed particularly notes that some memories are associated with emotions and other kinds of events that might strengthen or weaken the emotion or the memory for that event. And I think what Saeed is suggesting is exactly how the brain works. So those memories that are acquired at a time of increased brain vigilance, which often comes with a heightened sense of emotional processing, tend to be more indelible and more resistant to degradation over time. And this probably relates to connections from structures in places like the amygdala that send projections into the hippocampal memory system. And we know, for example, with memories that are formed in states of nervousness or anxiousness or even outright fear, those often can be very powerful memories that can stick with us for a very long time and might actually be associated with some disturbances of our mental health, as we all know. And the mechanisms there seem to be projections from the amygdala back to the hippocampal formation. And when those connections are active, the memories seem to be laid down with greater efficiency, and greater probability of recall. Now, thankfully, this doesn't happen very often, right? Because we don't want to be burdened by the details of everyday life. The example Saeed suggested was remembering what you ate for breakfast. We would much rather remember the person we fell in love with and the events around that moment of discovery rather than what we ate for breakfast. And so the emotional context is critical for establishing a memory that's likely to be more long-lasting. Now, even with that said, memory formation is not 100% efficient. We still have the degradation of memory over time, and we still have the fractionation of memory as memories move through the circuitry of the hippocampus from acquisition through consolidation and ultimately through long-term storage. So those are just a few thoughts that I could share. We certainly could say more, but perhaps we need to move on to another question. So Saeed, thank you so much for joining us and for asking two very interesting questions. I wish you all the best as you carry forward with medical neuroscience. And maybe I'll see you at one of our neuroscience meetings someday as you might pursue your interest in the field of neurobiology.
Thank you very much for answering my question and for this amazing course.
You're welcome. Thank you. How about if we go to Shadrach? Shadrach, are you there?
Can I hear you?
Hello, Shadrach. Would you like to ask a question? I'm afraid I can't hear you.
Can you hear me now?
Yes, I can. Thank you. Go ahead.
I have 5 main questions, but I'll ask as we go on. But I'm going to ask 2 for now.
Okay.
All right. The very first question is human brain uses as much energy as A, the mainframe computer, B, the laptop computer, C, the 10-watt light, D, electric iron, or E, a GMC car. Which one do you think will be the energy of our brain?
You're putting me on the spot, Shadrach. I do not know the best answer. I might be inclined to go with either C or D, but you tell me. What's the answer?
I think our brain travels at the speed of light. You know, the message that's sent across from maybe me touching something that is hot, and then the information that travels fast into our brain for it to reflect on whatever we touch. What do you think? Is it a 10-watt light or a 20-watt light? That's what I want to know.
Well, it sounds like you're maybe asking a question in 2 different contexts. One is about the energy consumption of the brain, and then you're also alluding to the speed at which the brain processes information. Right. Now, I think the energy demands of the brain are significant. About 25% of the blood that leaves the heart goes to the brain, and perhaps about that much of our overall consumption of energy goes into firing key enzymes and metabolic processes within the brain. So the brain truly is very energetic and very costly in terms of our overall physiology. Now, with respect to the speed of transmission, the brain is remarkably slow, I would say. So it does not operate at the speed of light. There's actually significant processing time that's required for signals to be generated and to be transmitted from one place to the next. And then at the synapse, there is a delay of about 0.5 milliseconds. Now that seems like a very, very short period of time, and of course it is, but when you consider the trillions of connections in the human brain, and the fact that each one takes a certain amount of time to process, suggests that there is a significant delay in the time that it takes for neural circuits in the brain to do their job. And one interesting upshot of that is that we're always living just a little bit in the past because of the time that it takes to process information. But the brain is a wonderful predictor of the future. So the brain can generate predictive models for executing behavior in real time that compensates for this relatively slow processing that takes place. So I know I didn't directly answer your question, but maybe that helps provide a bit perspective. Shadrach, I can't hear you again. I think you're muted.
Can you hear me now?
Yes, thank you. Go ahead.
How about comparing the brain to an electric iron or the laptop computer? Because electric iron, you see, maybe if you want to, the portion of our brain that is responsible for, let's say, smell or taste. You see, when it triggers, it becomes hot. And then you know that this portion of the brain is what you're using for this particular moment. Can you compare the brain to that? Because I'm coming from a psychological background. I'm a psychologist, and one of the tests or one of the practice that they did with an animal, with a monkey, to trying to test the portion of the brain that is responsible for, let's say, jumping from one place to the other. They were able to do that to one of the portion of the brain to know that this is the portion that he used if you want to jump from here to here. So is it that can our brain also be compared to that? Because a typical example will be if you are studying, your brain becomes very hot because that portion of the brain that you are using to study becomes very hot, especially if you are doing a lot of consumption. So I would like to know if we can compare that to like electric iron or laptop computer, which has hard disks and memory and processor in them.
Well, you're asking a bit of an abstract question, I think, using some concrete examples, comparing the brain to an iron or a laptop computer. I suspect that the laptop computer might be the better metaphor, but it's an imperfect metaphor, as would be any metaphor to a material substance that is of our own creation. I think one reason to appeal to the idea of a computer as a metaphor for understanding the brain is the nature of parallel processing, which is something that's going on in the brain all of the time. We're constantly processing in parallel information through a number of different channels. It is impacting the way the brain is functioning at various levels. A few of them are we actually well aware of at the time in which that information is being processed. And this is where attention and other mechanisms germane to cognition are so important in helping us filter out information that's less relevant to guide behavior at any one moment. But that information is constantly flowing into our spinal cord and through our brainstem and through our special sensory systems associated with the cranial region. So all of that's happening all the time. Your metaphor of appealing to an iron is interesting. Of course, all of this information is being processed, and that is, again, energetically very costly. And so there is some value, I think, in that aspect of the metaphor. Shadrach, I think I'm going to have to ask that we move on to someone else who's waiting to ask questions. And I know you have more questions, but maybe we can come back to you later on in the Hangout. Okay, so thank you so much. And why don't we go now to Kartik. Kartik, am I saying your name correctly?
Kartik, can you hear me?
Kartik, yes, very well. Thank you.
Great. I've been really enjoying this class, and one of the things that I really like is how you bring your knowledge of just so many different aspects of how the brain works to help us understand not only how the structures work by themselves, but also how they are related to each other. I think it's really valuable, particularly for me as I'm reading these research papers. It helps me get a better idea, okay, this structure is here, but it connects to this over here. So once again, I really appreciate that systemic aspect of the course. My question has to do with consciousness. And I've been reading a lot about this topic for a while, but recently in recent research papers, there's 3 areas that I'd be curious to get some of your comments and insights on. One is the claustrum, another is the posterior cingulate cortex, and the other one is the precuneus.
Okay, thank you. Kartik is asking about the claustrum, the posterior cingulate cortex, and the precuneus. Let me first address the claustrum. I had an interesting discussion about the claustrum just last week with a group of students that I was teaching here on campus, because we were looking at a brain specimen, and this was a human brain specimen, and we had just a beautiful look at the claustrum, and I was asking any of the students if they knew what this was, and of course none of them knew what it was, because it's a rather obscure part of the brain, until Nobel laureate Francis Crick and his collaborator Christoph Koch wrote a fascinating paper about the claustrum some years ago, in which they were suggesting that it might actually be really important for supporting consciousness. One of the puzzles about this part of the brain, which is actually located just between the insular cortex and the putamen. For those of you who have worked through Unit 3, I think you can possibly visualize this as I'm describing it, between the insular cortex and the putamen. It's a bit of gray matter that sits within the white matter that otherwise separates the cortex from the basal ganglia. The claustrum maintains connections with the cerebral cortex in a series of cortical-subcortical loops. And no one has really understood exactly what this part of the brain does. And I think Koch and Crick hypothesized that these loops that run between cortex and claustrum might be very important in creating the kinds of associations that would seem to be important for supporting consciousness, where otherwise we have so much distributed processing that somehow is bound together. So one of the early ideas about the claustrum was that perhaps it's a circuit that helps the brain solve what is sometimes called the binding problem, which is how can we have a unitary percept when the individual circuits that are processing the various dimensions of that percept are so broadly distributed across the cerebral mantle. So that's what little I know about the claustrum, but now I'm driven to want to know more, so perhaps I'll have a better answer for you at our next Hangout. The posterior cingulate cortex is an interesting part of the brain. It's receiving quite a lot of attention these days, as it's part of a network which is also related to the precuneus, which is just posterior to it, which is part of what we consider to be our default mode network. So, which is to say, if you think about what is it that you're looking at, or I'm sorry, what it is that your brain is working on when you're truly doing nothing, these parts of the brain tend to be very active. And so one idea is that the precuneus and probably part of the posterior cingulate is particularly inwardly focused, as opposed to externally cued or externally signaled. So if one is truly doing nothing, of course you're never really doing nothing from a metabolic standpoint. In fact, when you're doing nothing, your precuneus is one of the most active structures in your brain. And that's a bit of a conundrum. But what we do understand is that as we shift our attention to more externally focused stimuli or externally directed thought, then the activity in these parts of the brain seem to diminish. So this has led to this idea that these structures participate in a kind of default mode of brain activity when the brain is not engaged in particular tasks that have a cognitive demand, either because we are engaged with the outside world or we're engaged with some sort of abstract reasoning type of problem. There's more I could say about the posterior cingulate gyrus, but I think I would need to have a bit more confidence in the details by consulting some sources before replying more. We actually have I have some colleagues here at Duke who are studying this part of the brain and putting microelectrodes there, recording from behaving rhesus macaques while they are engaged in various tasks and trying to understand exactly what is the neural code at work as animals, and presumably ourselves, make decisions based on information that's processed internally but also cued externally. So some of that is happening there as well.
Great. Thank you very much.
You're welcome. Thank you, Kartik. Okay, let's see. I think that I'm sorry, your name is kind of small, but Natalija? Am I saying that correctly? Natalija?
It's Natalia.
Natalia, okay,
Yes,
great,
yes.
Thank you.
First, I would like to say hello from Slovenia in Europe.
Oh, thank you.
And that I'm really honored that I can actually ask you a question. So my
Well,
question
thank you.
is, I'm sure you know the Nature Methods newspaper, right?
Yes.
So every year they select a method of the year. So I was thinking to ask, if you had to pick one method in neuroscience, which one would you choose?
The method of the year, that would be a very difficult choice because there are so many advances in so many different domains. I'm tempted to suggest that the method of the year has something to do with brain imaging, but it would be difficult for me to say exactly what aspect of brain imaging I would put at the top of my list. One of the challenges with this notion of the method of the year is that I'm somewhat even opposed to the idea of declaring something a method of the year because it puts the emphasis on the method rather than on the science that is being discovered or being enabled by the method. And sometimes that's a problem in neuroscience research. We're too quick to apply a method without really having a well thought out question that demands answer with the particular method. So there's so much wonderful work going on with imaging methods that are using various means to look at neural activity at different levels, be it electrical activity or metabolic activity, or even whole brain imaging methods that can be used in human subjects. So there's so much to be excited about in the field, but I think we still have to be a little cautious not to be too quick to celebrate the method when we really should be focused on the important questions that need to be addressed. So I apologize if I sound just a little bit cynical about that, but I think that this is actually a bit of a problem in the world of neuroscience, particularly for those labs that are very well financed and very well resourced, where just tremendous technology is possible. I think we need to continue to insist that we focus on the most important research and not just what is now possible because of our methodology. So you must have a thought about this. What would you say is a candidate for method of the year?
I actually think when they chose in 2010 optogenetics, it was, in my opinion, a pretty good choice. Right now, I'm not sure. I'm kind of really interested in connectomics, but that's another question I wanted to ask you. What's your opinion? Because opinion is kind of divided. Like some researchers think it's. I also think it's too far for certain things to be claimed, but I think it could be very useful.
Right. I personally feel like connectomics is appropriate when we have a very well-constructed research question. So, for example, if one wanted to know what is the total input to a given population of neurons somewhere in the brain, because if we knew the answer to that question, we would have a deeper understanding of how the brain is organized and how it functions. So if we ask questions like that, then I think it's a wonderful approach, even as labor-intensive and as expensive as it is. Yes. But on the other hand, I don't necessarily think that there's great value in trying to describe the total sum of all connections that might otherwise be discoverable. So for example, we've known for some time, at least we've had a pretty good idea about the connectomics of a very simple organism like a nematode, C. elegans, for example. Yet I'm not quite sure we've gotten that far closer to understanding the behavior of the organism. So I think if we start with simple organisms so that we can begin to explore the challenges and the benefits of connectomics, we'll have more confidence applying it to more complex organisms. But I also feel like a more restricted application of this methodology might be very insightful and very appropriate. We just have to be very cautious and properly calibrating our goals.
Thank you very much for your answers.
You're welcome. Nice to meet you, Natalia. I'm not sure I've had a student from Slovenia yet in a Hangout, so it's nice to have you.
I don't think so, no. As I watched the older ones, no.
Okay, well, thank you.
Thank you.
How about if we go to Ahmad next? Ahmad, are you there? Perhaps Ahmad is not with us at the moment. How about Shahir? Are you there, Shahir? Okay, how about Soma? Soma, hello, I see you. I believe your microphone is muted. I can't hear you. Could you please unmute your microphone?
I believe Ahmad just responded back. Oh, wait.
Okay. Ahmad, are you there?
Okay, hello. Hello.
Yes, Soma. Hi, I can hear you now. Thank you.
Yes. Okay. Thank you, Dr. White. I'm very much pleased. I'm overwhelmed, and I'm very much grateful and thankful. I'm basically a housewife, but I'm enjoying your course very, very much. It is a wonderful course. Yes. Can you hear me?
Yes, I can. Thank
Sir?
you.
Okay.
Yes.
Okay. This is I can only want to say. Yes.
Well, thank you very much. Where are you, Soma?
Okay. Well, I have some questions. What is consciousness, and what is a dream? Why we're dreaming? These are all my questions. How it is related to nervous system? These.
Okay. Well, Soma is asking about consciousness and about dreams. Let me first just say a word about dreams. Dreams are a entrance into conscious experience, neural processing that's ongoing and that is under consolidation. So we tend to dream about events that are being processed as we sleep. And so there are memories that are being formed, and these memories can be activated in rather bizarre ways. So most dreams have an element of realism to them, but there's also an element of surrealism. And I think that reflects the fact that the brain is not conscious. We are asleep, of course, but the dream represents an activation or a recall of memories that are in the process of being laid down or perhaps long since stored that are being recalled in a rather unpredictable way. So one thing that we know about the dream is that it seems to be triggered by a burst of electrical activity in the pons. And this electrical activity hits the posterior thalamus and eventually is communicated to the posterior part of the cerebral cortex, which is the visual cortex, of course. And this probably is why so many of our dreams have a rich visual nature to them. But other parts of the cortex can also contribute. And so the quality of the dream typically reflects the participation of different cortical networks. Some dreams can have very clear auditory or even olfactory components to them, and they very likely reflect the recruitment of those cortical areas. Other dreams can be very emotionally charged. Some can even be quite fearful, and those probably reflect the engagement of circuitry associated with the amygdala in the anterior part of the temporal lobe. So this is just a little bit about dreams. There's a session later in the course in Unit 6 that talks about sleep and a little bit more on dreams then. Regarding consciousness, well, I think this is an unresolved challenge in neuroscience and in psychology and philosophy and the cognitive sciences more generally. No one truly has a satisfactory explanation of the brain basis of consciousness. The best that I could contribute at the moment is that there are multiple faculties of the brain that contribute to conscious experience. My sense is that consciousness is an emergent property of the brain, and that it will be very difficult, I think, to reduce it to the operations of individual neurons and their synaptic partners. But I do consider it to be a network property of the brain that reflects the contributions of multiple circuits broadly distributed in the brain. So I'm afraid that's the best I can do, is to give a very unsatisfying response to a very important and very significant question. So thank you very much, Soma.
Thank you, thank you.
You're welcome. I think we'll try Ahmad again. Ahmad, are you there?
Yeah.
Yes, sir, I'm here.
Very nice to meet you.
Hello. It's nice to meet you too.
Thank you.
It's my pleasure to see you, Doctor. I'm Ahmed Najjar. I'm from Syria, and I'm a medical student in my final year. I'm doing my USMLE's exam. I'm happy to take this course as a boost for my basic knowledge, and I'm being very honored to see you, sir.
Very good.
I have a couple of questions, if you don't mind.
Go right
First
ahead.
of all, I've been through a lot of knowledge through the deep understanding of the brain, and when I see this, I can see that the brain has like a sea. You can't go deep enough to understand every. So, what are we going next? All the brain soon? Are we going to live enough to long enough to see the brain fully discovered? I don't know what's our pace we are chasing right now. Is it enough for the research to discover all of this mystery?
Wonderful question. So Ahmad is asking about whether we will understand the brain well enough to really have a working understanding of the brain and ultimately ourselves. My hope is that this will happen, but it will require more time and more investment and more activity than what we're likely to see in our lifetimes. It's my hope for our children and our grandchildren that we may have a much more rich understanding of the human brain, that we can actually begin to change the way that we live in a way that optimizes our potential to flourish as human beings living in human societies. I think neuroscience can contribute greatly to the advancement of human flourishing, but I think it will be a slow process, and we need to be patient as we anticipate new discovery and new breakthroughs that can transform health, wellness, and human potential. One area, for example, that I'm particularly excited about is discovering the brain's potential for plasticity in the context of rehabilitation. So my hope is that we will begin to understand the rules of plasticity well enough that we can begin to reshape the way we try to help individuals with brain injuries and spinal cord injuries recover lost function. Now, there will be limitations, I think, because the brain is evolved to be a stable system, not a chaotic system. But I do think there is the potential to reshape connections for more powerful, beneficial outcomes than what we've seen so far. So I think that will be part of the future. And part of the future will also relate to what we do in education, particularly the education of children. So my hope is that we can understand better how the brain learns so that we can maximize the impact we have on young people while their brains are most receptive.
Another question, if you may.
Yes, please.
Actually, my future specialty that I'm interested in is the interventional neuroradiology, if you know about it.
Yes.
And so, what's your advice for me to prevent diseases in future in this precious brain?
Well, you need to understand the anatomy of the brain very well to operate in the field of interventional radiology. The general principle in medicine, of course, is that we do no harm, and for the interventional radiologist, that means that we do not damage parts of the brain that are important to support quality living and well-being of your patients. Now, sometimes some morbidity is inevitable because of the serious nature of the disease that you're trying to treat. And it's a very challenging and very demanding field to be in when you're having to make decisions about how much can one put at risk when you're contemplating an intervention. But the basic principle is to understand the functional organization of the brain so that you know what to preserve even while you're applying your interventions for the best possible outcome of your patients. Right now, much of that focuses on the region around the central sulcus, where we know that the body is mapped for motor control and for somatic sensation. We also know about language areas. We know about visual areas. We know about areas that are important for memory and emotion. But for so much of the brain, in the frontal lobe and in the parietal lobe and in the temporal lobe, we still don't quite know enough that would allow us to provide the best possible guides for interventional radiologists like yourself. But hopefully we will get there someday, and we can be much more strategic about the approaches that we take. Of course, new technologies will emerge in the years to come as well that will make, I think, your career more productive and more successful for the patients that you treat. So thank you, Ahmed. I appreciate your aspirations, and I wish you all the best as you pursue your dreams in medicine. So thank you for joining us.
Thank you very much. You are very nice. Thank you, Doctor.
You're welcome. Okay, how about if we go now to Shahir? Are you there, Shahir? I don't think so. So maybe we can go back to Shadrach. Do you have another question for me, Shadrach?
Can you hear me?
Yes, I can. Go ahead.
Okay. I would like to know whether you've heard of reflex action.
I'm sorry, say that again?
Have you heard of reflex action?
Reflex action.
Yeah.
Is there a particular reflex you have in mind?
Yeah, talking about the assignment that you gave us concerning the pathway through like touching a hard metal or the surface of a floor or something. There's a reflex action that I don't know whether it's psychology that I read or I read from a book that it says that it doesn't normally goes to the brain for it to come up. When it does something hot, it doesn't necessarily go to the brain for it to for you to show or for you to give you a feedback. Is that true?
It is true, yes, that there is information that is processed locally. So that's what we mean when we say reflex. But that information is also going up to the brain. So what's happening is that as we were to touch something hot, like if I imagine this camera is very hot, and if I were to touch it, I would immediately withdraw because the sensory signals are processed at the level of my spinal cord, and there is local circuitry that will cause me to withdraw from that hot structure. Now, that's going to happen at the same time that those signals are being passed through my anterolateral system on up to the brain. So I'm becoming consciously aware of the fact that I just touched a hot structure at about the same moment that I'm withdrawing from it. So the reflexes help us to coordinate our stereotypical behavior, which has obvious adaptive and survival value. But we also want to be consciously aware of the environment in which we're interacting. So there are these pathways that I've asked you to illustrate, like the anterolateral system pathway, that explains how it is that we become consciously aware of the fact that we might have just touched a hot surface. But again, getting back to your earlier question, processing in the brain takes time. So we don't want to have to wait to understand that we are putting our fingers at risk for being damaged on a hot stove before we withdraw. So there's great advantage to having a reflex that we don't need to think about. It just happens even before we become consciously aware of the potential threat or the injury.
Okay. Okay. Wow. That's good. I was really finding it difficult to understand that. Thank you very much. And also the other question, the function of the optic chiasm.
Yes.
Okay. In one of the examples or one of the practice that we did in school. Our lecturer said you should hit left, like if you hit your left arm, you feel it in the right hemisphere, and if you hit your right arm, you feel it in your left hemisphere. I would like to know whether it has something to do with movement or anything to do with neuroscience.
Yes, thank you for that question, Shadrach. The question that Shadrach's asking is about contralateral representation in the cerebral hemispheres. There has been some interesting threads in the discussion forums that you might want to look up about this question. People have, for many, many hundreds of years, asked why is it that the brain is organized for contralateral representation? And no one has a complete answer to that question. It may be that it is something of an evolutionary mishap that led to this organization. I tend not to think that way, but it's possible that there is an explanation of that sort. What I can tell you, though, is that almost every nervous system in all animals is set up with a contralateral means for representing the signals derived from the body and also for controlling the movements of the body. Now, in many animals, there's also some ipsilateral pathways, but they tend to be the exception more than the general rule. So, for example, in the visual system, we have an optic chiasm that allows for the information from our two eyes in the front of our head to be sorted so that in one hemisphere we see one half of the visual world and in the other hemisphere the opposite half, even though both eyes see the same regions of space. So in the demand of contralateral representation, we have to sort out the contribution of the axons from the two eyes. And for us, it's roughly about maybe a 52% contralateral projection and a 48% ipsilateral projection. But that's really an exception. Most animals have a much higher percentage of crossing fibers in their optic chiasm. And certainly once we are talking about animals whose eyes are more laterally placed on the head, the ipsilateral projection is very, very minor. So contralateral representation is more of the general principle of the way nervous systems evolved, with an ipsilateral representation being something of the anomaly. Now, I will say that the cerebellum is the big exception to all of this. If you've not yet gotten into Unit 3, you'll discover that the cerebellum represents the same side of the body, whereas the cerebral hemisphere represents the opposite side of the body. And that creates a bit of a challenge of connecting the appropriate parts of the brain to govern movement. So that's yet another question that we potentially could address. But thank you again for that question, Shadrach. I think we're going to move on and try to get a question from somebody else.
Can I ask the last question before?
Okay, sure. Go ahead. One last question.
That's my very last question.
Okay.
I'm around the Durham area. I'm in Burlington, and I don't know whether I can make a point to come visit you on campus or something like that.
Well, it's a very busy time of year for me. Maybe I can ask you to maybe send me an email, and we'll see if we can work something out.
And one last one. If somebody is doing the specialization, we have a specialization from Duke.
Yes.
That comprises of visual perception in the brain and then brain and space, plus the medical neuroscience. Can somebody use that to apply for medical school in Duke?
Well, you can certainly mention that these courses have been successfully completed, but most medical schools will require that you have courses taken for academic credit. And currently, these courses are not recognized by the Duke University School of Medicine as carrying academic credit. So this is a decision that needs to be made by each university as they look at the kinds of courses students are taking, whether they are online courses like this one or courses at a university campus. I think this is eventually going to change. I think more and more medical schools will begin to recognize the value of courses like medical neuroscience, but right now that value is not being validated with university credit. At least not here in the United States. There are some other places where students are earning course credit for medical neuroscience, but not here in the United States. I'm sorry to say, I wish that was not the case, but that seems to be what's happening now.
Okay, thank you very much. And,
okay.
Continue with the good work that you're doing. And
okay.
I'll send you a message and meet you on campus one of these days.
Okay, thank you, Shadra. Okay, let's go to Kenneth and see if Kenneth is there. Hello, Kenneth. Are you with us? Okay. If not, then maybe we can go back to Saeed. Are you still with us, Saeed? Is there anything else you'd like to ask?
Can you hear me, Mr. White?
Yes, I can. Thank you.
Thank you. Because of the low quality of internet connection, I couldn't ask my question very clearly. For example, for the first time, when we hear that we lost, for example, a member of our family, we will remember it for the rest of our life.
Mm-hmm.
And I have just postulated two kind of mechanisms for affecting our brain, and I just know if they are true or not. For example, when we hear that our mother, or I don't know, my father passed away, it has affected our brain really deeply, and it can make thousands of action potentials. Or maybe days by days, as the time goes by, we think about that tragic event unconsciously, without thinking about that. But we always remember the moment that we hear that, for example, sad news. Could these kind of mechanism justify for remembering a very special moment in our life?
Thank you for the question, Saeed. Saeed is again asking about memory and whether a very emotional circumstance surrounding that memory might be explained in terms of the intensity of the brain activity, the numbers of action potentials associated with that event, or might the actual act of recalling the event over and over again contribute. And I would say yes, both are very likely to contribute to making those kinds of memories, such as the memory of getting the news of the passing of a loved one. Both kinds of mechanisms are certainly at play. There are signals related to the emotional context in which the memory is being acquired that can enhance the efficiency of memory formation, and that is likely attributable to these projections from structures like the amygdala that I mentioned earlier into the hippocampus. There are also projections to neuromodulators, such as projections from the amygdala that affect the basal forebrain that produces acetylcholine, projections from the brainstem that release norepinephrine. So acetylcholine and norepinephrine can both enhance neural activity and very likely contribute to an increase in the efficiency of memory encoding that's happening in the hippocampus. Now, the other point that I would make is that I think your insight is very likely correct, that as we recall a memory, we have the chance to reinforce it. We even have the chance to modify it in subtle ways, and this itself is an interesting issue, how we can change our own memories by recall. But I think that the process of reliving that moment is an opportunity to reinforce that memory and perhaps add to it new associations as we continue to process over time. And surely this is partly what's happening as we pass through a period of grief. And so there's probably something quite powerful about that, particularly in this context of a very emotional memory associated with a real sadness in our lives. So I think you're asking excellent questions, and I think your inference and your intuition about it very likely has firm neurobiological foundation to it. So thank you very much.
Yeah, thank you. The reason that I asked the question again because I couldn't hear your voice very clearly at the first time. So sorry if I asked twice more.
That's
For
quite all
the
right.
second time.
I appreciate your patience with us. Okay, this is going to have to be a bit of a shorter hangout than most of my others because I have to get on to another meeting at the university here. But perhaps we can take one last question. Is there someone who'd particularly like to jump in with a last question?
Yes, sir.
Shadrick, I'm sorry, but I think you've had more than your share of questions in this particular hangout. Let me see if Shahir is there. Shahir? Okay. Let me go back to Ahmad. Go ahead.
Assalamu alaikum, sir. I want to ask about the process of the brain and how it's processing the informations. Now I am learning new languages, and they are telling me that if you are now speaking German and Spanish with the English and with the original native language, now you are like using i7 from Intel Atom, you know. It's like you have a new space that you are using in your brain that wasn't functioning. Is that correct?
Ahmed is asking about multilingualism and what happens when we acquire new languages, particularly in adulthood. Is it possible that we're using brain circuits that previously were not active or not engaged? I would say that that is not likely to be true. What is more likely is that we are repurposing connections that were serving other functions. So, for example, as we begin to learn new languages, we seem to be differentiating the circuitry in the lateral part of the temporal cortex that is encoding the language forms. And we sometimes think about Wernicke's area, for example, as being important for understanding language. Indeed it is, but one very interesting fact about this part of the brain is that there may be multiple nodes that are critical for the activity that encodes language, and there may be different nodes for different languages. So as you learn more languages, you are differentiating this part of the cortex. So it had been functional previously, but now you're forcing it to undergo plasticity and differentiate itself so that there will very likely now be important nodal centers that are governing the way this network is operating depending upon what language you are using. So as you are learning more and more languages, you can anticipate there to be this beautiful mosaic forming in the functional circuits of your lateral temporal cortex. One reason why we know this is that when certain individuals have to undergo neurosurgical treatments for problems in their left temporal lobe and their language areas are mapped, we can actually identify that there are distinct locations in this lateral temporal network that are critical for understanding different languages and different language forms. So I certainly hope that none of you ever have to undergo brain surgery, but if you do, you should insist that your neurosurgeon maps your languages, because it's your languages that are critically important for your quality of life. And there may be some surprises. There may be different nodes that are not where the neurosurgeon might anticipate, unless they are properly mapped. So this is something that happens at a medical center like Duke University, and I have a colleague here who does many of these procedures every week. And he is constantly being challenged with individuals that are multilingual because he knows that he has to take great care to identify what are the key structures that he needs to avoid. And for a future interventional radiologist, you'll have the same challenge, Ahmed. You'll have to make sure that you're aware of what are the key nodal points in the language networks of your multilingual patients. Okay, folks, I think I'm going to have to sign off here, but thank you very much for your participation, and I look forward to seeing you for the remaining weeks of medical neuroscience, and perhaps you all can join me for our next Hangout. we will find a time to do this at least once more, possibly twice more, before the conclusion of the course. So thank you all, and I wish you all the greatest success in the course and in the rest of your lives until we see one another again.
Thank you very much, sir.
Thank you.
You're welcome.
I hope seeing you again, inshallah.
Okay, take care, everyone.
Take care, sir. Salam.
Bye.
Goodbye.